Hey guys, welcome. Thanks for joining me today. We're going to continue on with our lecture 9, and then if there's enough time we'll get to lecture 10 as well, but we've still got time, so there's nothing for us to be concerned about at all. Welcome again. Well, but we've still got time. Okay, so what we're looking at today is our polar coordinates. Okay, so with our polar coordinates, so we think about changing frames, and changing frames basically represents a change from our normal Cartesian coordinates, okay, to our, oops, we're going to draw on that, to our, so there's our 1, there's our origin, there's our 0, there's our 0, 0 origin, okay. So we use a transformation to go from Cartesian coordinates in terms of x and y, okay, to our polar coordinates, which have a representation in terms of r and theta. So instead of being in terms of x and y, they're r and theta. So there's a slight difference in the way that we think about these coordinates, and so we've got to get used to them. Now it's going to involve a bit of exact values trig and all of that stuff that you've kind of used in the past. If we do a resolution for r, we'll get a value of r equals the square root of x squared plus y squared. So that kind of thing. Also from these guys here, it's not hard to work out that tan theta is rise over run, y over x, okay. And so what we're able to do is using these basic translation ideas, make a change from a point xy to r theta and back again if we need to. So the recognition of how these things go together is sometimes a little bit not obvious, so we've got to spend a little bit of time just getting to know some of those ideas. So for our thetas, we could go all the way around, so we could have a domain that's 0 to theta 2 pi, or we could have minus pi, but there's usually a constraint or a restriction on the interval, and that would be then just plus pi, okay. Okay, so alright, so what we'll do is we'll have a look at the next part. In terms of our integration over this polar plot, this is our polar plot here, instead of doing our integration dx dy, we'll be doing it in a new frame involving r and theta. So I haven't written it directly because there's a little bit of development that needs to happen. So this one's fairly straightforward, we get that idea, okay, but here there's a little bit of development that we have to build up, if you like, to get our dA, okay. So we'll have a look at that. Alright, so if we take a look at our polar subpart, and we're having a look at this rectangle that's been pulled out of the polar part, so if we were looking at this part, we might say it's this little square here. Okay, so we want to have a look at the increments in the polar part. So there's our little square, and we've got an area dA. Okay, so we can consider that in our rectangular coordinates quite easily. Okay, so we've got our dx dy. For our polar coordinates though, we need to consider the impact of the new environment that we find ourselves in. Okay, so I don't know why they're quarters. Length of a small element is approximating to dr, and the width of a small element is r d theta. So we need to have a look at that. So if I take this and draw this down to its origin, and this one as well, we can see that they're going to converge down here. Okay, and so we'll have d theta so an increment in the angle theta. Okay, so we've got our full theta, and then we've got our increment adding. So there's our theta, and there's our d theta. So it's not easy to pull together without a bit of support there. Okay, and then we've got our dl. So if we think about our radius, so that's our r, and then we've got a little dr here. So this is the dr for this one, and our d theta. So on top of our r, we're going to have a dr, and our theta will have a d theta. Alright, so what does the area represent in here? What does this area here represent? And so what we've got is our r with an increment. Yeah, that's theta. Thank you. With our increment r, so our area is r d theta dr. Okay, so that's the area of this particular part here. Okay. Likewise, if we were to have dl here, r d theta. But this is the one that we're interested in up here. Okay. So in terms of dl, v sine, sorry, r sine theta, d theta, r d theta. Okay, so the area, that should be an equivalent. Oh, sorry, I shouldn't have let those quarters stay on there. That's just the way it's printing. So what this is, that dx dy is being translated to r dr d theta. So we've got a new frame of reference that we have to add to our integrals when we do those. Okay, so a new frame of reference that we have to put together for those. And when you first encounter this, it's not so straightforward. Students like to think of it just in terms of dr d theta, but we have to take into account the r of our length. If you want, you can put if you want a little okay, so if we go from x to r, so from Cartesians to polar, so we've got Cartesian to polar. I guess it's a good time, given that it is a little bit complicated. Why do we bother? Why do we bother doing Cartesian to polar transformation? Why would we do that? What's the reason that we do any of the integration techniques that we use? It's to make life simpler. Okay? So it's to make life simpler. So the only reason that we would do this is because in the Cartesian coordinates, this is just horriblest. But if we do the transformation using our r dr d theta, then we're likely to be able to have an equivalent that's quite a bit simpler. Okay, so what we've got here is functions of theta transposed over our Cartesian coordinates and the increments in our theta and r. Alright, so we make a change, that's the first thing we do, to r dr d theta. Now what you'll notice is that this here is dr, so that's regular in our thinking of an incremental change. d theta is incremental change. But notice this r is a new variable added in. So it'll be a product with anything that's preceding it. So it can be taken over and placed in front. If this has already got an r, then that becomes an r squared because of this guy existing here. So it just catches students unaware. Initially we need to be aware that we've got to have this r on top. Alright, so if we have a look at our function, so here's our integral for some function over dy dx, and then we do the transformation. So the first thing you'll notice is dy dx is transformed to r dr d theta. Now what about x and y? What happened to them? Well, what's the equivalent of x? We did that previously. If you look at the definitions that you learned back in high school, x is r cos theta and y is r sin theta. So we just make those substitutions. R cos theta, that's your x. R sin theta, that's your y. Okay, so we do this substitution, if you like, of equivalent forms. So the transformation involves okay, so the forms of the equations, the forms of the variables. Okay, so x is r cos theta, and so we've got our increments shown between the two regions. Alright, so let's have a look at our, let's just do this way, and think about integrating this particular segment, this shape A, given this way, okay? And we're given a Cartesian coordinate of function x, dx, dy. So we've got to go through and substitute for both of those. So we're going to have to substitute an equivalent form for x, substitute an equivalent form for dx, dy. Okay? So where we have an integral, sorry, I want to draw on this one. So where we have an integral for our a, x dx dy, I'm kind of spacing them a little bit, okay, we're going to have an equivalent. Now what's x? What's the equivalent form of x based on the transformation from Cartesian to polar? Well, previously we see it. So we've got our integral. X is going to be replaced with, yeah, thanks very much. That's it, r cos theta. What are we replacing? There's no y, so we're only doing x. What are we replacing dx dy with? Okay, and we've already got some idea of what the limits of integration are going to be. Okay, and so we've got r in terms of the radius. Okay, so 0 to 2. Okay, and so that'll be fairly straightforward for our inner. And then theta will go from 0 to pi and 4. 0 to pi and 4. Okay, so we're doing, that's our transformation. So we've done our transformation from Cartesian to polar. Now that one's fairly straightforward. Some of them get out of hand. Okay, some of them get out of hand. Now one of the things you'll notice in this particular example is that we've got numbers for our limits of integration. So we can multiply them by Fabini's and group them. Okay, so we can write, we don't have to do the inner outer. There's nothing wrong with us doing the inner outer, by the way. We can do the inner outer but to simplify it, it might be just as forthright to invoke Fubini's, and in that case what we'll do is we'll do the r's together. Now r times r will be r squared dr, so that you can cross them off if you like, just to make sure you got them all out of the way. And our radius is 0 to 2, multiplied with 0 to pi on 4 cos theta to theta. So Fubini's has been invoked, and we're doing the product of the integrations. We could have done inner, and there'll be other occasions where we can do inner, but I just wanted to show you that particular example. Okay, so you can make life a bit easier if you can. Okay, so for our part here then, what are we going to do? Up and under. Now the differential of sine is cos. The integral of cos is minus sine. Okay, so we've got minus sine. Remember that this is a product, so just be careful here. This is not a, let's just put a big product sign there. Minus sine theta between 0 and pi on 4. So we have to do our substitutions accordingly. So we've got 2 cubed on 3 minus 0 cubed on 3 times minus sine pi on 4 minus sine 0. So just take your time and make sure you get each of those parts. Okay, and make sure you get your groupings. So for the algebraic part, that'll be quite straightforward. Okay, so that's gone. That was a sum, so we're left with 2 2s and 4 2s are 8. Okay, and we're multiplying it. Now this guy is asking for an exact values trig. What's the y at pi on 4? What's the y at pi on 4? So pi on 4 is here. So it's the one that's got the same length there and there. So the y is 1 over root 2. So it's minus 1 over root 2. And what's the y at 0? So here's our 0. And what's the y there? The y there is 0. So we can kind of forget about everything out of here now, because sine minus 0 is just minus 0. So what we've got here is 1 over root 2. Now you're going to find doing the polar rectangular stuff, if your exact values trig is not up to standard, that you're going to find it a little bit tricky. Okay, I wish I could make a shortcut or give you something that will help you, but if your exact value trig hasn't been worked through, then unfortunately it's a bit problematic. So what we end up with is now differential of sine is cos, so the integral of cos is sine, and I put a minus there. That's very naughty of me. So that's a plus. So we get 8 on 3 root 2. The usual convention is to take the surd off the bottom. So we'll multiply that by 3 root 2. Okay. That would give us 24, 8 root 2. I should have done that perhaps back here. I always make things more complicated, don't I? Trying to tell you to make it simpler. So what I might do is I might just do the root 2 here. So 1 over root 2 is going to be root 2 over 2. So it's the same thing, root 2 over 2. So that's 8 on 3 times root 2 over 2. That's probably easier to bear. Okay, so we get a little bit of cancelling going on. So we'll get 4 root 2 on 3. Okay, so a little bit of extra work there to work through. Just watch your integrals, make sure you take your time. Okay, alright, so it is possible, and I've put all of that on the computer, so I'll post this afterwards, but on the computer the printout obviously doesn't explain anything, so you jump to those areas straight away. Alright, now we could get some Cartesian coordinates that have some very horrific style problems in them, so we would be grateful to be able to change and transform the system so that we can move to, so I'll just bring it to here, and we'll think about this integral on the bottom here. Wow, what a horrible integration. Okay, so we've got a circle, we've got the limits of integration, so we've got for x, which is on the inner. Okay, so let's have a look at the domain. We've got minus the square root of 1 minus y squared. Minus y squared, x, and square root of 1 minus y squared. Wow, so that's an interval, okay, and y is simply 1. So these intervals represent the half circles. So x squared plus y squared is a circle with a radius of 1. Okay, and these limits are the piecemeal parts. So in other words, they're the bottom half and the top half. Okay, the bottom half and the top half. So we need to recognize that this region is in fact a circle of radius 1. And we go around radius 1. Okay, so from that we can see that integrating this, putting these into our by FTC parts, wow, who would, that's rather difficult, isn't it? Okay, that's rather difficult. So what we want to do is try and do a transformation of this into our components. So we've got our dx dy, so that's going to become r dr d theta, and then we've got our x squared and y squared components. Now who can tell me what x squared plus y squared would look like? Okay, so x squared plus y squared is going to be in its alternate form. Here we go, change forms now. So we've got r cos theta squared plus r sine theta squared. We know that that's going to be r squared cos squared theta plus r squared sine squared theta. We can take the r out together. R squared cos squared theta plus sine squared theta. And so who can tell me what this is? Who can tell me what that is, please? Who can tell me what that is, please? Cos squared theta plus r squared theta. So if we've got our rectangle, yes, thank you. 1. So in actual fact, by doing the transformation, we have simplified this. Okay, so this guy here is going to get translated to r squared. Wow, that's really made it simple, hasn't it? Okay, so we've got our 0 to 1, and we've got our 0 all the way around 0 to 2 pi. Okay, so we can build up our integral using this information. So we're going to have r dr d theta. Following our routine, x squared plus y squared is substituted for x squared. Our r is 0 to 1, and our d theta is 0 to 2 pi. How easy is this? And again, you can do this thing. Now notice there's no theta terms here, so if we do Fubini's, it's going to look a little bit odd, but that's okay. We'll do 0 to 1. Now notice that r times r is r cubed, dr, multiplied by the integral from 0 to 2 pi, the theta. Now you know what that means. I pointed this out to you last time. You know what this is here, okay? You know that that is effectively going to conjure a theta. Where there isn't a theta, there will be a theta. If that was t, so on and so forth, okay? So in this regard, we've now done our transformation and moved all of our parts over, and how good are these? Okay, so now it's up and under, so we get 4 over 4, I forgot to do that last time. Okay, and then we've got our, what are we conjuring here? So we've got theta, haven't we? Between 0 and 2 pi. Okay, so that's just a straight substitution in numbers. Okay, so we've got 1 over 4, subtract 0 over 4, theta, which is 2 pi, minus 0. So that's obvious. So this is 1/4, that's gone, that's gone. So we've got 1 over 4 times 2 pi. And so we get a cancel. So we get pi on 2. Okay? And that's our final result, pi on 2. So the transformation process is a bit tricky in picking your geometry, doing your equivalence, and making sure that you redraw so that you can get new limits. Okay, now I've done all of that on the computer side, so this is where it just jumps out at you now. Well, wait, what, where, who, what? There's my r dr d theta. That's the substitution for r2 according to this other work up here. Okay, that was all of that. So those things aren't always obvious. So if you find yourself struggling a little bit, how do we get to that point? It's probably not as complicated as you think. So they are interesting and they are doable, but it's you've got to be patient with yourself. Okay, so let's have a look at another application, and let's think about that. So use polar coordinates to evaluate an improper integral. Now, why are we able to do an improper integral? Because we're going to rely on the fact that the function has this decaying property. Okay, this decaying property. Okay, so we're going to rely on that. Now, what can we do to make things a bit easier for us? Well, it turns out that, now you're going to say to me, where did you get that from? Well, okay. So it turns out that this also has an equivalent form. And if I put in y, that they are the same. Okay? That's helpful. Why is it helpful? Okay? Because we can, and this is so I also. So if I just kind of put a bit of a dotted line across there, so that's also I. So one of the techniques we'll use here is to see these properties and use them together. Okay? Okay, so what we're going to do is come over here. I'll just start a new page, I think. So to make life easier, we're going to I squared. Multiplied, so remember that there's a multiply because I'm doing Fabini's here. Okay, so now we've got something where we can think about our index rules. Okay. So what we can do is use our index rules What's the rule? We can sum them. And we can put the dx and y together. Okay, so all we've got to do is take the square root at the end and we can make this into a pretty straightforward integral. So the integral we're looking at doing is replacing a single integral with a double integral by squaring okay. Now it's not obvious why we're doing it, I get that in terms of experience, but we're using two integrals, a single integral and a double integral, to overcome the difficulty of dealing with this improper integration. Okay, so we're able now to make a transformation from our double integral in x dy to our integral in r d theta. Now, what is this guy up here? Let's look at our parts. We've got r dr d theta, and then we've got this bit up here. So minus x squared minus y squared. Is that not the same as minus x squared plus y squared? Is that not the same as cos squared theta plus y squared theta, sine squared theta? Is that not the same as r out the front squared minus r squared? Is that not 1 again? So this whole thing here is going to become minus r squared for these reasons. Okay, so it's our transformation. So let's do our transformation, remembering that we're still doing I squared for the purpose of dealing with the indefinite integrals. Sorry, yeah. Okay, so what we're going to have here are the new integrals, e to the minus r squared r dr d theta. Okay. So our RDR is going to take its leaf from x and y with r going to infinity. Whoops. Okay. And we're still going to go 0 to 2 pi. So 0 to infinity, so that's 1. We don't know what that is, so we're just going to have 0 to infinity. Okay. And we'll also have 0 to 2 pi. Okay. So that's reduce the complexity of what is ostensibly a quite complicated integral. Okay. So, what have we got to do now? Well, we've got a little bit of work to do. This is not straightforward by any means because of this chain rule. This is a U substitution. Okay, so we'll use the U substitution idea to help us forward with that. So in this case we'll do the inner, even though because we've got to account for this part here. Okay, so the first thing we want to do is integrate 0 to infinity e to the minus r squared rdr. So that's what we're looking at. Okay, so we've got to do a u substitution. Okay, so what's going to end up happening is we're going to swap these around and we'll get minus a half du equals r dr. Okay, so there are our substitutions. We're substituting these guys. Okay, so we're going to have minus a half integrate du. That's our u substitution. I know it's not straightforward, but the beauty of it is e to the u. Aha, that was the goal. The goal was to make that simpler. Okay, so we've made it simpler. We've also got to just check our integrations using function notation. We've changed our limits. 0. So we've got minus infinity squared and minus 0 squared. So we've got 0, and we're just going to have so it's just minus infinity, isn't it? So where before we had a 0, and now we've got a minus infinity. Now that makes sense because we've got this decaying part. Okay, so it's going to decay to 0. Alright, the next thing we want to look at is we want to have a look at is something that you would have known from school. Show the area of a circle is pi r squared. So I guess here we get to use a transformation to show that the area of a circle is pi r squared. So we've got an integration over its domain, okay, and we are going to do a conversion from our x, y Cartesian coordinates to our polar coordinates. Okay, so there's our region. Now the way that we'll do that is that we'll transform dx dy into r dr d theta, so it's fairly straightforward. Our r is 0 to r, so there's our 0 to r, and theta is going to be 0 to 2 pi. Okay, so you can see that it's a fairly straightforward. Now because it's all in numbers, all we've got to do is split them. Okay, so we'll split them and operate on both of those. So that's up and under. It's r to r, where we substitute algebraically, and this one will be simply 2 pi minus 0, so we'll get 2 pi, so that's your product. Okay, that one is just 2 pi. So we get the substitution for r, so we get 2 pi over r squared, the 2's cancel, and you're left with the area of a circle is pi r squared. So I don't know, it's now you know how to do the integrations and the transformation. It's a very straightforward integration. No big deal there, but a very interesting idea. Alright, so the next thing we want to do is have a look at the general change in coordinates. Now what I'm going to say to you is that this is a bit of a white knuckle ride. You know, when you hang on tight, whoa, hang on tight. You might have thought you've been hanging on tight at the moment, but no, that's not the case at all. So in this case here we can do the matrix transformation idea where we have our x and y. So there's our origin and x Okay, and we find some value 1, 1. Okay, and then we look at making a transformation. Now you can see what's going to happen. We're going to be using a chain rule, okay, to get this transformation to this point here, 1, 1. Okay, so we would like a way of writing dA equals dy in terms of new coordinates. Okay, so that's an understatement. So basically what we've got in our transformation of our 1, 1 coordinate, so I'll just put that back up. Okay, and our 1, 1 is this one. Come on, where are you? Our 1, 1. And so the area element from x, y, so that's our coordinates frame of reference, to st, we use this thing called the Jacobian, and you guessed it, this is the det. Okay, this is the det form, and you'll notice that you've got dx ds, so there'll be an equivalent, dx ds, dx dt, dy ds, dy dt, and we've been able to do that. So that transforms this coordinate system using the Jacobian. Okay, so where we'd have our domain in fxy to dx dy, okay, we'll now have a double, and the double will look like this, and we'll have x s of x and then we'll have y, sorry, I want to change that to a comma. So then we'll have y s at t, that's better, y ds dt. Okay, so we've got this transformed integral. So it is a bit of a white knuckle ride. It's something you're going to be, no, I wouldn't do that to you. Okay, I won't put a Jacobian in this course because we don't have enough time to spend a lot of time on this stuff. We would do it in a normal full course, and analysis is a subject that does that, but because half our course is statistics, we won't be putting that into your examination. So you can go, whew, okay, that's fine. Alright, so just an example, Cartesian coordinates. Okay, so if we go ahead and do all of this, we'll end up with r cos squared, this is this multiple, minus r sine squared, okay, and then we can take out the minus of minus is a plus. Okay, so we've got r cos squared plus r sine squared. We can take r out as a common function. Yeah, it's very tricky to recognise that as 1. Okay, and yeah, so we get okay. Alright, so we can expand this idea further. Alright, so the next, and we can do Cartesian to elliptic coordinates, and we can use an elliptic transformation. And here's our transformation alternate forms. I know you're smiling, aren't you? You're going, wonderful. Okay, but we can, believe it or not, we can manipulate all of this to our advantage. So we can go for the theta, usually 0 to 2 pi, also v, which is our positive. Okay, so we can, in terms of our formula, we've got x squared over a squared cos squared u plus y squared over a squared sine squared So that would be our base equation that we would be able to manipulate in order to do substitution of similar forms. Okay, so we would be able to do that. So x over a cos u is cos d, and y over a sine. Okay, so then we can use these as our transformative information. So building up the dy dx equivalent, and so we get this du dv. So this is our new transformation pairing. Okay, and you'll notice that the slides stop there. Okay, so we can do more advanced coordinate swaps in order to make transformations between different systems, not just Cartesian to polar, but to elliptic coordinates as well. And really, the sky's the limit. So there are subsequent courses in maths that you can do that don't have the tie-up with stats the way we have this one tied up. Advanced maths and calculus would be advanced calculus. Advanced maths and physics would be subjects that would cover more of this in depth. Okay, so we're at 4:30. So what we're going to do is that's taken us to the end of 9. So we're going to finish there with 9, and then we're going to jump on to 10. Okay. And we'll have a look at triple integrals. Okay, so for triple integrals, we want to integrate over a volume, over a region in 3 dimensions. So integrals in 1D are defined as a limit over a sum. So this is revision again, that you're familiar with this in terms of its Riemann sum. In 2D, our double integral has an equivalent I and J, Riemann sum. And now we go one step further and we define our integral in 3D as a limit of sum, not just as areas underneath, okay, and doing areas, but boxes. The boxes are the elements of integration for a triple integral. So our change in volume is not just x and y, it's also z. And so the Riemann integral looks a bit more complicated, but I think you're getting the gist of how these things are put together. So we've got x there, this one was y, and the vertical one's z. Okay? So as the number of boxes increase, the limit of the slices goes to infinity, and so we can see this grow and subtract with smaller and smaller, infinitely small boxes to get our coordinates. So we probably won't get through all of this today, but it's worthwhile making a start and getting it out of the way for us in case we've got particular things we want to focus on for revision. Alright, another way of writing this is to write it as a triple integral, and notice the change. It's no longer a region, it's a volume. Okay, so that's often what you'll get, and then we've got the limit for our volumes approaching 0 for all of the boxes. That is, the boxes are going from a bigger size to a smaller size, infinitely small. Okay, and that's this idea here. Again, we've seen this before for our double integrals. Again, we just look out for that. Okay, there it is. Notice the difference. This has got your function in it. For these guys, what's going in here? Okay, not this, but we understand what that means now. Okay, and so we can look at it that way. Alright, so for some application it lends itself to a volume of 1. Alright, as in 2D, the integral can be computed iteratively. A rectangular box in 3D is described. So these will be simpler ones. We wouldn't give you a nightmarish transformation, for example, polar transformation or other. But yes, you can do all of that with triple integrals. So what we would do is look at keeping it simple, probably where you'd be able to invoke Fabini's. Okay, the order isn't important. Okay, if there's numbers in the limits of integration. All right. So the reason that you'd swap them around is to make it simpler. Okay. So for x, that's our A and B. For our y, which is out the back here, we've got C and D. And then for our back corner and our top corner, we will have P and Q. Okay, so we're using those out the back, so just that C should be out the back here. Okay, so probably the best thing we could do is have a go at an example. Okay, integrate the following. So we've got x, y squared z is our function. Okay, dx, dy, dz, where b is a rectangular box with the following. And you'll notice they're simple number equations. So they've been allocated their respective x, y, z integral limits of integration. So x is being put at the back, 1 and 2, because Fabini says the order is not important. Okay. Y is being put in the middle, 1 to 3, and 0 to 1 for z is going in the middle. Okay. So if we do the integral 0 to 1, then is there a z? Yes, there's a z. Okay, 0 to 1, so that's pretty straightforward. Dy. Okay, so provided you recognise that you can invoke Fabini's first to change the order, and then you can invoke the multiplication of the terms, you can simplify something that looks pretty horrific. And we don't ask you to go much beyond that. That's actually about as difficult as it gets. Okay, so for this guy here, up and under, we'll end up with z squared over 2 between 0 and 1. We'll get y 3 over 3 between 1 and 3. We'll get x squared over 2 between 1 and 2. So we'll get 1 squared over 2 minus 0 squared over 2. That does that guy. So that's a half. This is 3 cubed over 3 minus 1 cubed over 3. So this is a product, so this is going to be 3 3s are 9, 3s are 27. 27 divided by 3 is 9. That's a third. So that product is 9 minus a third for that one. For this one here, we've got 2 squared over 2 minus 1 squared over 2. 4 over 2 is just 2. 2 minus a half. So just be careful with all of your fractions and what are you adding and summing and what are you multiplying. So this is a half. So that's got to be 27 on 3 minus a third. That's got to be 4 minus 1 over 2. So we've got 4 3 to 12. Oh, we can cancel some of that, I guess. Why don't I do that? I always go for it, don't I? Sometimes I'm better off just pausing. So 2 will go 13. So I'll be left with 30.2, and that's your answer. Alright, so it's possible to do them, but use these techniques to help you, okay? Where they get harder and harder, and we'll do that now, but I'm just making a bit of a point. If we did do something like for an exam, this would be the type that we would use, okay? We would use it so that we'd only have numbers in the limits, and so then you'd be able to do that. So I put the computer printout there. Okay, so we'll kind of draw a line there with that asterisk and say that's about as hard as it gets. Now it could have e to the whatever in it. You'll see that in past papers if you look. But at this point, it won't be like one of these guys. Okay, so describing more general regions in 3D. In a 1D region, we describe it by an inequality. In 2D, we looked at a pair, an outer and an inner set of inequalities. Okay, and in 3D, we need an extra pair of inner inequalities to describe the domain. So we've got our A to B, our G, and the convention is we use U with Z. And you'll notice the order is going up, constant, function of 1, function of 2. Okay, just note that as it goes on. Okay, so we've got our 3 parts. We've got our constants for A and B. Then we've got our G of X and G of Y. Okay, our G of X and G of Y. And then on top of that, we've got our surface, which is this guy. So the upper part is this bit, and the lower part of the surface is this bit. So it's a bit more complicated. That's a bit of an understatement, isn't it? Alright, so then if we integrate over a 3D domain, look at the form of the equation. We've got a 3-value function, x, y, z. We've got dx, dy, dz, and then we put in our domains so that we've got our complete set. Alright, so it would be reasonable for us then to do an example. That would be reasonable for us to do that. Okay, so let's have a look at an example. Oops, we'll stop there. Okay, so in this particular example, we've got to do a little bit of geometry. So we have to interpret our parts. So we've got x equals 0, we've got planes. X equals 0, y equals 0, and z equals 0. And we have another plane, give it in this form. Now you can plot that using technology if you want to. You can plot the plane to see what that looks like. But ostensibly what it means is we're going to have our x, our y, and our z. From the origin we'll go, x will be 1, 0 to 1. Y will be 1 minus x. So 1 minus x will be this line. One minus x is this line. 0 to 1 minus x, that way if you like. And then we've also got z is 1 minus x minus y, which will be up here. So we've got a tetrahedron, which is effectively a rectangular pyramid that's sitting on its point, or sitting on one of its faces. Okay, so that's the 1 minus x part. and so we've got a few little manipulations we need to do in order to get each of these guys out. Okay, so so when z is 0, you'll get x plus y equals 1. That is, y is equal to x minus 1. There it is. Okay. Sorry, I've done that wrong. I've written x minus 1. It should be 1 minus x. I don't know why I did that. Okay. 1 minus x. Alright, what else have we got? We've got when y is 0, we're going to have x plus z equals 1. So z will be equal to 1 minus x. And we can otherwise arrange this as z equals 1 minus y. Alright, so we're getting our limits from the basic geometry of our planes, and that's very difficult. I want to acknowledge up front that for you guys to put that out and organise that in that way is very, very difficult. You'd have to go through and think very carefully about your planes, your points of intersection, what your lines are, and all of that stuff together to generate this set of domain integrants. Once you've got that, then you can go ahead and put your integral together. Okay, so integral together for this one, it looks like this. So there's our z dy dx as our z function, and then we've got our integration limits have been added. Okay, so z, y and x. Okay, so all you've got to do then is follow your rules. These are now filled with functions, so you've got to do your inner, and then you'll do your third one, and finally you'll do your outer. So you must do it this way. You can't invoke Fabini's. There's no trick around this. You've just got to do the hard yards. So the inner one will be an integral between 0 and 1 minus x minus y for z dz. So just be careful how you put this on the page. Alright, so the integral is going to be up and under between 0 and 1 minus x minus y by the fundamental theorem. And so we'll get z will be 1 minus x minus y all squared minus, on 2 minus 0 squared on 2. Okay, so the second term is algebraic, so it's gone, and so then we get our next part. Now, is it easier to do something with this or to leave it as it is? Because it's going to go inside the next integral, and the next integral is 1 minus x. So sometimes it's worth trying it. We can pull the half out the front, so that'll simplify it a little bit. We've got 0 to 1 minus x. That's this guy. And we're doing dy. So we'll just do dy, and we've got 1 minus x minus y squared. Now you can do the expansion if you want to. Okay. But we'll see what that brings us. Okay, so we'll end up with a half. Now if we do I put the 2 over here. I just brought the half out, which is fine, I can do that. Okay. No, that's alright, that's fine. I don't get everything right, Lucas, so it's good. So what I want to do here is think about this 1 minus x minus y, and if I multiply that through by minus 1, I get y plus x minus 1. Well, in either case, I might just do it as it is. We're going to end up with a negative, I think, anyway. So the minus would be, okay, so let's just do that. Alright, so for this one here, that would be a u substitution. Okay, and the u is going to be all of this with respect to y, and you're just going to come back with a minus 1. Okay, so I'm going to take the minus 1 out, and then we'll end up with 1 minus x minus y cubed over 3 between 0 and 1 minus x. So that's the integration completed for that middle set. Okay, so then we've got to put our terms in. So we'll get minus a half. Now, what are we doing dy? So everywhere there's a y, we're going to substitute that. So we'll get 1 minus x minus bracket 1 minus x divided by 3. So you've got to take care. Okay, and then minus 1 minus x minus 0. That should have been cubed. And that can be cubed. And the 3 can be taken out too, can't it? I think the 3 can be taken out. Okay, so I'm going to have to continue on the next page because I think I've run out of space. Okay, so we've got so 6. I'll put that as 6. Okay, so inside here, got 1 minus x minus 1 plus x cubed over 3 minus 1 minus x cubed over, no, take the 3 away, Jason, you've done that already, you've accounted for that. Okay, so what have we got here? Minus x plus x, 1 minus 1. Okay, so that's becoming 0. And so all we're left with is minus 1/6 minus times 1 minus x cubed. So the minus times a minus makes for a plus. So we'll just get 1/6 1 minus x cubed. Okay. Okay, now that goes into the final integral. Okay, and the final integral so we're going to have 1/6 integral 0 to 1 dx and it's 1 minus x 3. Okay. So if I convert that around, I'll get a minus back. Okay, so it's a little bit easier to process. Alright, so we're going to get a negative again. So we're going to end up with just a positive, u substitution, u equals, so that'll be just 1. This will become 4. Wow. So this is 0, so that term's gone. And this is minus 1 to the power 4 over 4. So it's an even, so it's just 1/4. Oh, 0 minus 1, yeah. And so I've got 1/24. Okay, that's what I've got. But we can check that using Wolf. Okay. Okay, so we're going to explore another version. I'm just wondering about the time. So I'm just checking. I'm going to leave. Oh, yeah, I'm going to leave cylindrical coordinates until next week. So we'll have a look at cylindrical coordinates next week, and that'll finish off. That'll finish off the course for us. We've still got quite a few to get through, about 20 slides, so that'll be fine. Okay, there's a bit of problem solving that goes with that, so I want to make sure we get that right. Okay, I know your heads will be full. Just try and take note of where I've suggested where it's pertinent and useful. Don't get too hung up on the complexities, because if you spend a lot of time at this end of the course, in this last week and a half's bit, it'll probably rob you of where you need to develop other stuff as well. Okay? Alright, so just stick to your plan, stick to your platform, and you'll be fine. Alright, I'll see you in the labs. Thanks everyone for coming along. Bye now.